Hello everyone, my name is Bo Yuran, a PhD candidate from the University of Queensland. Today I'm going to present our work about dynamic structural clustering on graphs. This work is completed together with Junhao Gan, Hao Wu, and Anthony Wirtz. There are many variants of graph clustering algorithms, such as correlation clustering, modularity clustering, structural clustering, and etc. An interesting feature of structural clustering is that in the clustering result, clusters may overlap with each other. And as a result, vertices may play different roles. Some are cores, hops, noises, and etc. In a protein-protein network, structural clustering can be used to identify functional models. And it can also be used to detect communities in social networks. And since some vertices may be noises in the graph, it can also be utilized to detect voice. Structural clustering works on an undirected graph G, where n is the number of vertices and m is the number of edges. We use uv to denote an edge between vertex u and v. And u and v are called neighbors to each other. And we define the neighborhood NU of a vertices U to be a set that contains all U's neighbors and U itself. Here is an example. The neighborhood of vertex V4 contains vertex V1 to V5, and the neighborhood of vertex V9 contains vertices V6 to V12. By intuition, if two vertices share a large number of common neighbors, they tend to be similar to each other. But how can we measure how two vertices are similar to each other? We use structural similarity sigma UV in structural clustering. Here are three popular definitions of structural similarity in literatures. You may notice that no matter which form of definition we adopt, computing a structural similarity all requires us to compute the size of intersection between two neighborhoods. And when the size of the neighborhoods is large, the computation time can go to ON worst case time. There are two parameters in structural clustering. One is epsilon and the other one is mu. We can label an edge UV as similar if and only if sigma UV is no smaller than epsilon. We call edge UV a similar edge in short. A vertex U is called a core vertex if and only if U has at least mu similar edges incident to it. Here is a running example of structural clustering with epsilon set to 1/3 and mu set to 3. For vertex V7 and V9, the intersection of their neighborhood contains vertex V6, V7, and V9. And the union of these two neighborhoods contains vertices V6 to V12. So sigma V7, V9 equals 3/7 and is larger than 1/3. So it is labeled as similar. The same is for edge V9, V10. In this graph, I mark all the core vertices and similar edges with color. To construct a structural cluster, we start with a core vertex, for example, V3 here, and we include all the vertices similar to V3 into the same cluster, namely V1, V2, and V4. Since V4 itself is another core vertex, we then include all the vertices similar to V4 into this cluster. That is to say, V5. And V5 is not a core vertex. So the process terminates and we obtain one structural cluster. Follow similar process, we can obtain another structural cluster in this graph. Here you may notice that vertex V5 belongs to both clusters. That makes it a hop vertex that bridges these two clusters. And vertex V10, V11, and V12 belongs to no cluster. That makes them noises in this graph. From the above construction process, it can be seen that given a valid edge labeling, the structural clustering result can be output in O(n plus m) time with traversing the graph once. So the bottleneck of the state-of-the-art algorithms all lies in computing a valid edge labeling. To compute a valid edge labeling, the state-of-the-art algorithms need O(m) to the power of 1.5 worst case running time, and they require O(n plus m) space consumption. However, when it comes to the dynamic scenario, maintaining a valid edge labeling becomes challenging. To see this, here is the above example. If we delete edge V6, V9 from this graph, the edge labeling status and the clustering result may change significantly with the deletion of one single edge. Here is an example. After deleting edge V6, V9, similarity between V6, V9 and their neighborhoods all changes. So we call V6, V9 an affecting update for the edges incident to V6 or V9. And we say these edges are affected by V6, V9. Take V7, V9 for an example. After deleting V6, V9, sigma V7, V9 becomes 2/7, and it is smaller than 1/3 now. So the label of edge V7, V9 flips from similar to dissimilar after the deletion. In fact, all the edges I marked in color here have their labels flipped after the deletion. So if the neighborhood size of V9 is large, to maintain the labels of these affected edges may cost O(n) worst case time cost. To summarize the problems that the state-of-the-art algorithm face as the curse of neighborhood scanning. As I mentioned above, to compute structural similarity between two vertices may take O(n) worst case time cost. And worse still, even if we treat the computation as free, it may still take O(n) time to maintain the labels of the affected edges. To overcome the O(n) barrier, we introduce row approximate notion that has already been used in other clustering problems. Given a parameter epsilon and rho, for an edge UV, we define its valid label with respect to row approximate notion in the following minus. If sigma UV is no smaller than 1 plus rho times epsilon, it means that sigma UV is far larger than epsilon. UV must be labeled as similar. And if sigma UV is smaller than 1 minus rho epsilon, it means that sigma UV is far smaller than epsilon. Then UV must be labeled as dissimilar. Otherwise, if sigma UV lies somewhere between, it means that sigma UV is very close to epsilon. It falls into the don't care case. It can either be labeled as similar or dissimilar. They are all correct. What's the benefit of the row approximate notion? The first one is that we don't have to flip the labels of the affected edges as frequently as before. The second one is that we can use approximate similarity instead of the exact one in our problem. Here is an example. We set rho equals 1/7. Although sigma V7, V9 changes from 3/7 to 2/7 after the deletion of edge V6, V9, it is still no smaller than 1 minus rho times epsilon. So it can still be labeled as similar after the deletion. In fact, with row approximate notion, the deletion of V6, V9 affects no edges label. So we can save the time to maintain the labels of the affected edges. For the approximate similarity tailed sigma UV, we can compute it with bounded error 0.5 times rho epsilon with probability 1 minus theta in O log n to the power of 2 time. And under this approximate similarity, an edge UV is labeled as similar if and only if tilde sigma UV is no smaller than epsilon. Although we have row approximate notion, the problem is far from solved here. The reason is that we still have to maintain the approximate similarity between each pair of vertices to maintain a valid edge labeling in the dynamic scenario, which won't help us to break the ON barrier. We still need to take more advantage of the don't care case in the row approximate notion. We define update affordability here. For an edge UV with sigma UV equals A over B, here A equals the size of intersection of two neighborhoods, and B equals the size of the union of these two neighborhoods. If we insert an edge UW, there are two cases. The first one is if W is already in the neighborhood of V, then the size of the union of these two neighborhoods won't change, and the size of the intersection is increased by 1. So sigma UV is increased to A plus 1 over B. And if W is not in the neighborhood of V, then the size of their intersection stays the same, and the size of their union is increased by 1. So sigma UV is decreased to A over B plus 1. And the same is for delete an edge UW. We can prove that an edge UV can afford at least K affecting updates before its label flips. It means that if UV is labeled as similar at this moment, then within the next K affecting updates, we don't have to compute the approximate similarity or maintain its label. It can safely stay similar until the K plus 1's update. Upon the K plus 1's affecting update, we need to calculate tilde sigma UV and maintain its label. Now the question becomes, how can we capture the K plus 1's affecting update? A naive solution is to maintain counters on each edge to count the number of affecting updates. However, since a counter can be affected by updates that involves either of its endpoints, we need to maintain these counters individually. For example, if an affecting update that involves U comes, we need to increase C1, C2, C3, and C4 all by 1. We notice that such an affecting update affects the value of C1, C2, C3, and C4 equally. So our goal is to use one single counter to count the affecting updates that involves U. To achieve this goal, we use the technique called distributed tracking. Here is a running example of the basic idea. Here we set the update affordability K equals 8. And each endpoint has a counter CU and CV initialized as 0. And each counter is assigned a budget lambda equals K over 4. Here lambda equals 2. And a coordinator on the edge will receive one report whenever a counter increases by lambda. First, everything is initialized as 0. When an affecting update involves U comes, CU is increased by 1. And if another affecting update involves U comes, CU becomes 2. And since CU has increased by 2, the coordinator receives one report. And if an affecting update involves V, CV is increased also by 1. Then, after another 2 affecting updates involves U, the coordinator has received 2 reports in total. So we say, here is the end of one round. At the end of this round, we calculate K prime as K minus CU minus CV. Here K prime equals 3. And then we reset everything to 0 again, and we start a new round with K prime. This process terminates when k prime equals 0. As a result, all edges incident to the same vertex can share the same counter CU. And we use a main heap on U to organize all the budgets assigned to U. Then when I'm affecting updates, UW comes, we only need to increase CU and CW by 1. And then we let distributed tracking technique to decide which edge needs to recompute the approximate similarity and needs to be relabeled. Putting the above techniques together, we have achieved the following results. For every update sequence containing big M updates, we achieve this amortized cost for each update with probability 1 minus delta star. And if big M equals n to the power of some constant, we can achieve indeed O log n to the power of 2 amortized cost with high probability. At all time, our data structure requires On plus M space consumption. And we can output the structural clustering result in On plus M time. For the clustering quality, we can guarantee that the clustering result of our row approximate clustering lies somewhere between 2 exact clustering results. We offer the sandwich guarantee. And when we set rows sufficiently small, the approximate clustering result of our algorithm, it can be very close to the exact clustering result. Please refer to our paper for more details on this sandwich guarantee. We further develop our algorithm to support cluster group by query. Using the above technique, we can output the structural clustering result in On plus M time. And when the size of the graph is large, On plus M time is also very large. So in this query, we can group vertices in a subset Q based on their cluster IDs. The motivation is that sometimes people are more interested in a subset than the whole clustering result. So for our results, we guarantee the same amortized cost for one update, and the space consumption of our data structure remains On plus I time. And we can output the cluster group by query result with a time that related to the size of Q. So when the size of Q is much smaller than M, this time cost is much smaller than On plus M. This is all of my presentation. Thank you.